doing this now.
And
so
the fact that I can go back to questions makes it also a lot easier.
yeah. So looking at this, so it's like, which of the following correctly describe the simplified MCDE for solving carrier densities, or at times greater than or equal to 0 is what it says in the actual problem, but this one just says greater than 0, but that's just how it is. So here's the trick though. So it's multiple choice, so it makes it sort of easier, but it also makes it harder because he's going to try and trick you. Because looking at this, hello, Michael. Oh, Michael's on his way in.
Oh.
What's up, Michael?
What's up?
Hola. We're just going over my my practice quiz. Yeah, but this is before, because I have, like, obviously as part of this we're gonna make a formula sheet. So I have the PowerPoints that are going to be on this test to pluck the formulas out of, and we can also go over the homework solutions as well. Oh shit.
Have you guys looked at it much yet, or no?
Looked at what?
Like the material in general.
I have a lot, yeah.
Okay, cool. I haven't touched it at all.
There it is.
So
looking at this third question, so this is also going over like what to expect on the actual test itself and like tricks, because obviously there are some tricks involved here. Like this one, question 3, he includes like change in n and change in p, or the excess carrier densities. But your equation, this question says ND, so our majority carrier is ND. So if we're doing an MCDE equation, it's all about the minority, so it should only involve p. It should not ever touch n. So when we get down to question 3 here, and we're looking for an MCDE question that's simplified, oh, we got the punch too. We got Ethan. We got Ethan number 2. He just joined.
Oh, nice. Hi there.
He's muted.
Mm-hmm.
My gosh, you have so many inbox messages. That would drive me crazy.
Oh, I don't even. I'm never gonna change this. I refuse. No, we lost him.
Go for it.
I refuse. But so looking at this, the trick with this is, since obviously we're looking for the minority carrier, your equation should not have any form of n in it at all. And that goes if we were given p as majority, then it shouldn't have p at all in the minority. It should only have n's. So we look at the first option. Well, also here's the first thing you need to know. But obviously, I don't know if he's going to change up the answers, make it more difficult. This really makes it like obvious. But let's look at this. So what should be like canceled out of this question? So we're looking at it. It says consider a uniformly doped silicon crystal. Uniformly doped is important to know because that means there might not be any spatial dependence.
Right.
And then following parameters just gives us some values. It says it was in the dark and under thermal equilibrium. That's important for a couple of the questions, but that's like last chapter stuff he's just throwing for free points. And then here he says at time greater than or equal to 0, a light source with uniform illumination, yet again, that means no spatial dependence, is turned on, resulting in optical generation rate throughout the volume, yet again, no more spatial dependence since it's everywhere at once. And then answer the following questions. So that means that our MCDE is not going to have any spatial dependence, and we can cut that out. So here he made it easy because every single answer had spatial dependence cut out. That part in the middle with the d, p, or n times your derivative squared, dp squared, that thing. That big one in the middle. That cuts out here. But I anticipate on the test it'll be harder, to where he won't just give you all the correct simplifications. He'll give you a bunch of the wrong ones with different stuff canceled, and also do what he did here, which is move around n's and p's wherever, and also pay really close attention to the tau, because that's also important, because p, tn, that's wrong. This one's almost correct, except for the fact that the tau is n and not p.
Right, because it's only n's or only p's, right?
Yeah. So whenever you simplify an equation, it should only have p or n depending on what the minority was. If it has anything that isn't p or n, it needs to be uniform across the board. If it has any type of mix and match, it's a wrong answer. That's one thing to just understand about the equations themselves. But I anticipate it won't be this easy, because looking at it this way, he already canceled spatial dependence everywhere. So that makes it a lot easier, because you can look at this, and if you know the general form of the equation, which you can have on your formula sheet, you can pretty easily just know the answer is D. Because if you look at the formula sheet and you get rid of that middle term, it just becomes this, and that's it. So that's just like, that's the first part. Because if you do this wrong, technically every other part, like if you picked, let's say he didn't cut out spatial dependence and it was in there and you like, oh, it's the one with spatial dependence, and you picked that and you worked with that throughout the rest of the test, every other question will be wrong. So this question is extremely important for when you do the test.
Right.
Because if you mess this one up, it's game over. The rest of your points will be off, assuming you actually use your answer from this question to solve the rest.
Yeah. How many questions were on the practice quiz?
This had
14.
14 questions. I did it without a calculator and in 17 minutes, and I scored a 50.
Okay, that's not bad.
It isn't bad because then I went back through it and I figured out all the mistakes. Like, look at this one, question 2. I treated n as ni, which was wrong. It's just 10 to the 18th divided by 10 to the 18th becomes 1.
Yeah. So I may have been thinking of a different class, but last practice quiz, we couldn't go back and look at our stuff, right?
I think no, it was through Respondus. So I think you could, but you had to look at it through Respondus. So it made it a lot stupider. This one didn't need Respondus at all, and it was a lot easier to like mess around with.
Cool. Yeah.
Oh,
I'm
yeah.
still gonna look back on this like 5 times.
Yeah, the one thing I really I wish he did allow us to do though was I wish he allowed us to take it more than once. You only get one attempt, but then it immediately shows the answers. I don't even care if it showed the answers. I'd still like to do it again, just like with the calculator. Yes. But like this one, and then moving on to this next portion of it, it's asking initial condition stuff like it did on the homework. Like part B or C was always like write out your initial conditions. So it's saying what is the initial condition for the MCDE in terms of like t at 0. So you scroll up to your top, and it says here, where does t at 0 equal? That's going to be here. So it's not just going to be like question 1 where you can use like regular rules because it was at equilibrium. It's going to be at the part where there's actually a light source on. So we have to treat it as such. So looking at it, at the light source is immediately turned on. In that instant is turned on. That's when it started. But it's been given absolutely no time to actually, generate anything. Since it's been given no time, its graph starts at 0 here. The graph starts at 0 and goes up until it reaches the carrier concentration, which is going to end up being GL tau P. So that's what your graph would look like. And since that's what the graph would look like, your initial condition ends up being just 0, as it says here. You start at 0, 0. But that this type of question changes depending on what you have up here. So it's like remember when he said like it's going to be more like the homework with less theory, like in the presentation and everything. Here this is theory. Like this is still pretty much theory. Because here, let's see what we would do. Actually, not really. You could also use the formula to solve for it if you wanted to, because here's your correct answer right here. So, well, this is the correct answer of this is the simplified, and this ends up being your solution. In order to get this, you would need the solution version, which is, I guess, why he put them flipped, because it would make more sense for this to be question 4 and this to be question 5, because you can use this to answer this. But that's not what he did here, because obviously he's trying to show that this is something you can just know intrinsically by reading the problem. You don't need to do math here. But when we get here and we like simplify it and everything, this is like the standard form of simplification you'll see. This is something you can put on your formula sheet. This is the simplified without spatial dependence. This is what it ends up looking like. Because the A value for the general form always ends up being GL tau P. So yeah, so this is what it's always going to look like. So this is a formula sheet thing. We'll talk about that later when we go through the PowerPoint presentations to build a formula sheet. This is what
Are you like giving a lecture today?
I suppose. I do this in Cal C because what I'm trying to do is I'm building a case. Well, this also helps me because talking about it like ingrains it in the head. But like I'm recording it for the students so they can see it later, because obviously not everyone can attend, and then I can go over and rewatch it. But it also gives me like something I can send to like the past people and say, look, I already was basically a past leader. Please give me a job. If that ever arises, is something I would like to do. All right, so now we can get down to like this one. So does everyone understand how like this MCD was simplified? Because we have the PowerPoint right here where he actually just, nope, that's not it. Wait. No, this is it. Yeah, this is it right here. This is the stuff he was talking about. So the general solution when the spatial derivative is eliminated is this, bottom part with the AE plus GLTP, but A always ends up being equal to GLTP or tau P. It always ends up being the same thing. So if you pull out a G, like a GL tau P from both terms, it ends up becoming this every single time. So instead of like on your formula sheet, it'd be more beneficial to write this down than it would be to write this down. Because this still takes some doing, because you're going to sit there and be like, oh, how do I solve for A? When in reality, it's actually just going to end up being this every single time. So this is a quicker thing to have. And then we get to like number 6, and this is another one that's actually easy, but it was just a mistake on my part, because I went through this and every single wrong answer on my quiz was simply because, look right here, I didn't multiply GL by tau P when I did the rest of the calculations. I only took it as GL. So I was off by a factor of 10 to the 6th every single time, which caused problems. But I went back through.
Hold on. If you say you're off by a factor of 10 to the 6th, doesn't question 6 have the correct answer as 100?
It is 100 here. Let me see. It's because of this part. Here, let me check it. I have the calculator with me. Because tau P in this problem was 10 to the negative 6 seconds.
Mm-hmm.
And GL was 10 to the 18th. So I was always plugging in 10 to the 18th, but I should have been plugging in 10 to the 12th, because 10 to the 18th times 10 to the 6th ends up being 10 to the 12th. So I was off by that factor, but because of the way the equation works, because here it's at time 1, you're using this equation.
Right.
So you end up with your P ends up being, or the way I did it wrong, would end up being 10 to the 18th, 10 to the 18th minus that. And at 1 divided by, 10 to the negative 6, that's paramount to treating it to some absurdly large number. So you can just say it's big. And if it's big, a big negative in, the exponent of E ends up turning to 0, essentially 0. So I ended up saying that, what is it? I ended up saying that what? Because then this is also multiplied by that. So 1 minus essentially 1 to the 1, or 1 to the 0. No, it becomes 0.
Okay.
I'm like 90% sure I actually should have had this right. I think I just failed to type in the 100. Either way. Just for reference, I remembered later on that I messed up there. So any like numerical issues that are similar to this question was because I did not multiply by 10 to the 6th, because I'm a doof.
Okay.
So don't make the same mistake. And then we have something similar here, but not exactly the same, because look, this is still 1, because this is the same question as this. N and ND are the same, and they will continue to be the same because it's the majority carrier. It does not change, or any changes are negligible. So this question at time less than 0 when it was in equilibrium, and the question down here where it was at time is equal to 1 when it's no longer at equilibrium because there's a light source, it's still going to be 1 because the majority carrier has extremely negligible changes. So these questions are the exact same question. Question 7 and it was, I think, question 2 are identical. It's just with like different wording to sketch you out and everything. And then this,
real quick.
Yeah.
I just came here. Could you kind of like go do like a review of like how you started, or I guess I could just watch the recording or something?
No, I got that. That's fine. So we can go back up here and do that, because I think everyone like jumped in around question 3-ish or 4-ish. So either way, so that's quick and everything. Because here, so this one's asking what's the hole density in the crystal at t less than 0. So if we go back up to the question, t less than 0, the sample was dark and under thermal equilibrium. So this entire thing is basically saying that this part of the problem is what we've been doing in like the last homework and like last quiz topics. This means that we can use the law of mass action, which is n times p is equal to ni squared. And using that with our majority carrier being nd 10 equals 18, it's going to be 10 to the 20th divided by 10 to the 18th which just gives us 10 to the second or 100. Because remember, you can't
Okay.
type in on the quiz. He told us this. You're not able to type in like 10 to the second or 10 to the 10th. You always have to type in 1000000 or 0.00001, which is stupid, but we're gonna have to do it. It's kind of annoying. So
that
that's
is
gonna
pretty
be
annoying.
it is annoying, but
So-
you always have to do it like this. And then down here, this was, as I said, question 7 and question 2 are technically the same. Just like it would trip you up if you didn't understand that the majority carrier is unaffected in an MCDE question. In all instances of an MCDE question, the majority carrier should be unaffected.
Okay.
Okay.
So like the ND is never going to change. It should always be the same. Like the number, the ND or the MP, whatever was given to you, or the NA, whatever was given to you at the beginning is going to stay the same regardless of change. Unless there's some factor that like deliberately tells you that it changes, like in the question. Like if there's something broken or something like that, which might
Okay.
happen. But like this one, like it's the same explanation as last one. This is equal to this, so it just ends up being 1. I got this wrong and said 0 because I approximated to 0 because I treated this like NI, so I thought it was 10 to the 10th divided by 10 to the 18th, and I said that's small enough to be 0, so I put 0. So that's not right. Don't do that. And then this part, question 3, is the initially simplify the MCDE. So on the formula sheet, it's definitely going to be a good idea to write down like the full non-simplified general form of the MCDE equation, which is this plus the spatial dependency in the middle, which in this instance gets canceled away. And like earlier, I explained the fact that this question 3 on this practice quiz is a lot easier than I would expect him to make on the actual test. Because here, every single option is correct in the way that the spatial dependence was eliminated. If we go back up here, the keywords you look for to eliminate spatial dependence: uniformly doped, light source with uniform illumination, throughout the volume of the crystal. All of these things are hinting at the fact that this question has no spatial dependence. Everything is happening everywhere at the exact same time. And because of that, you can eliminate spatial dependence. But in question 3, you look at this, every single answer has spatial dependence removed. And I think that makes this question a lot easier because we're allowed to have a formula sheet. If you have the like traditional full non-simplified MCDE equation on your formula sheet and you just cover up spatial dependence, you can immediately know which one of these is correct. Because the only thing he's doing between the questions is either changing signs or putting in the wrong thing. Like this, we're looking for all P's. Like he'll sneak like a tau n or like a change in n somewhere, and that makes it wrong. It has to be all P's. Change in P here, change in P here, tau P here, since it's minority. So this is a lot easier than I would expect him to do on the test. I feel like he's probably going to have it to where like maybe like this has spatial dependence in it and this has spatial dependence in it, and then like you have to figure out which one is right. So there's a chance for you to simplify wrong. Like if you didn't pick up on the fact that spatial dependence goes away and you pick the wrong answer, that's going to result in every single, well, next question, every single part of the question after that is going to be wrong if you're using the wrong formula. So that's not good. But luckily, like these are going to be pretty easy since we have a formula sheet. As long as you can just read the question properly and understand the like the keywords to get rid of stuff, it shouldn't be too bad. And then like initial condition stuff here. See, this is something you can solve for using this, but this obviously comes after this. So what that like tells us is that this type of question can be done without a calculator. This is just theory. So if we're looking at something that was in equilibrium, therefore there were nothing being generated, no light was on, and then you somehow turn on a non-equilibrium state by, you know, lighting it up, your carrier is going to go from 0 up until it reaches like the saturated carrier density at the what is it? It's not solid state, at the steady state. At the steady state, once it reaches steady state, it's going to be GL tau P. But the thing is here, we don't know this equation yet, theoretically. Obviously, if you really wanted to, you could do question 5 before question 4 and get the right answer anyway. But you can look at this and see that at time 0, there hasn't been enough time for any type of carrier to be generated. Because remember, we have such thing as carrier lifetime. It's a small amount of time, but it still requires time to occur. So no carrier can be generated or recombined without some amount of time. So at time 0, you generate 0. Nothing's had enough time to, generate or react to the light yet. So it's going to be 0. And this is for something that goes from, this is obviously going from dark to light, but this can be the reverse. You could be in a system where we've been lit until we've reached steady state, and then he takes away the light, and it's going to go down. So you're in that point at time 0 where the light was taken away, your answer, as opposed to being 0, would be GL tau P or GL tau N or whatever the question asked for. So when it comes to like this, yeah.
Real quick, I'm getting a lot of white noise from somebody's mic. Could I don't know whose that is, but
Is there anyone?
Hit stop.
Here, I'm gonna turn off my mic. Maybe it might be my fan. Let me check. What do I? Meeting my mic's difficult. Did it go away?
yeah, it did.
All right, I can turn my fan off. But the problem with turning my fan off is my light goes off too, so I'll be in the dark.
Sorry about that.
I mean, I
okay.
can see. It's just
Okay.
that I look like a crazy person because my monitors light me up, and I look like a ephemeral spirit or something.
Nah, I like crazy people.
Yeah, I'll do that. I can turn my brightness to 0, and it's still perfectly acceptable. All right, white noise gone and everything.
Ah, there you go.
Yeah,
Here.
I mean, I think so. Well, I mean,
Yeah,
Yeah.
we'll see. So like this type of question, the initial condition questions, is like wholly based on your understanding of the original word problem. So I wish he gave us more of these in the quiz, like several quizzes, because obviously he gave us one quiz with just this problem, which is comparatively, like if you did the homework, this is pretty similar to, I would say, something like problem 1, like one of the easier ones.
Mhm.
Like problem 3, problem 4, those are the types of questions that I feel like he might slap at us at the test, but we'll see, obviously. But we can go over the homework as well to see how to attack those properly. So this part, when it's simplifying, this is a general solution, which is something you can just write down on your formula sheet. So this doesn't take much doing as long as you simplify it right, which also doesn't take much doing if you have the formula and know what to look for. So question 4 and question 3, these types of questions can essentially be gimmies as long as you understand like the keywords for simplification and wrote down the answer on your formula sheet. That's how you do 3 and 5. And then these ones were, I explained earlier, that was on me, but like pretty basic stuff. You plug in 1, this goes to 0 because of that. This goes to 0 because of that. Because it's at some large integer number. It's some integer number divided by a very, very small number, that being 10 to the negative 6. That goes to some large number, which is negative, which brings this to something close to 0. Turns this to 0, it just becomes GL tau P. GL tau P is 10 to the 12th divided by Ni, which is 10 to the 10th. That just becomes 10 to the 2nd or 100, which is the right answer. And then down here, yet again, same exact question as question 2. 10 to the 18th divided by 10 to the 18th is always going to be 1. Majority carrier will not change in an MCDE question because that's not what's being asked about here. It will never change. And then we have calculate the net recombination rate at t less than 0. Obviously, t less than 0, as the question stated, is equilibrium, stuff we've been doing for like the last 2 chapters or whatever. This means that there is no net recombination rate. There is a formula for that, though. The net recombination rate formula, I believe, is just GL times like your tau value. But I think it was in a PowerPoint, so we'll go over that later. So obviously beforehand at equilibrium, there is no recombination rate. It's just 0. But then here's where it gets a little weird because I don't actually know why this answer is like this, but I might actually, never mind. So calculate the ratio of the net recombination value divided by GL at t equals 1 second. So now this is just saying that we are at some time and we're at the net recombination rate. So we have to solve for R net and we already know GL. So R net is given in a formula. I think it might be up here. Yeah, right here. So this is under a non-equilibrium state, which is what we're currently at in this question. And you can know you're in a non-equilibrium state if this doesn't hold. If the law of mass action doesn't work like it worked in question 1, then you're no longer at equilibrium. So we know we're not in equilibrium, so this is what we have to do to solve. So holes are minority in this case, so we use this version of it, which just how happens to be, this is going to end up being 10 to the 12th, as stated previously. So that's some, 1 second. 10 to the 12th divided by tau p, which is 10 to the 6th in this question, is going to end up being 10 to the 18th. Yes. So that's going to be 10 to the 18th. So 10 to the 18th as your R net. 10 to the 18th divided by GL, which in this question also happens to be 10 to the 18th, is 1. And that's how you get the answer. Don't know why he gave us, a margin of error of 0.01 on both sides, but 1 falls squarely within that. So that's how you solve for this type of question. And the R net is given as a formula for either, electrons or holes. So we can write that down on the formula sheet when we get to that later. And then this is a similar question. So find the values of P, or find the values of like P over Ni at T to the -6th. So you see how my answer is like 63 million, but the correct answer is 63 and 64. Yeah, so this is where my previous mistake of not multiplying by tau p really shows up, because my first two numbers are right. It's just the fact that it's to some ridiculous power of 10. So we can do this question the same way we did the others, except we're given a new time value here, which happens to be 10 to the -6th. So this is our new time value, and we're looking for p. Everything ends up coming back to this part, which is question 5. So obviously you're just going to plug in 10 to the -6 up here. Everything else is already a given constant that you know by now. Or, well, no, not even know by now, or just straight up given in the problem. So if you plug in 10 to the -6 up here, divide it by 10 to the -6 right here, that's going to be 1. E to the -1st now. So now you have e to the -1st. And if you use a calculator, 1 minus e to the -1st is just some random number. It's 0.632 whatever. So this, what you can do is you can do 1 minus that number, and then you can multiply that number by GL tau p. GL tau p, which as we know by now is 10 to the 12th. And that gives us some other arbitrary number that has 3.67 in it. And then you go down here, back to the question.
Just out of curiosity, how long are y'all going to be on this?
We're almost done with the quiz. There's only like 4 more questions. And once like we're done looking over the quiz and everything, I guess we can go immediately to making a formula sheet, since that's something that's pretty important. Obviously this is going to be recorded, and I'll send a link to the full thing if you're not able to attend like the whole thing.
Well, yeah, I've got another review session at like 7:30, so.
Yeah. So that's fine. So it'll all be recorded anyway, so it won't be an issue, because our test is what? It's on Tuesday?
Yeah.
Yeah, I have to, the way I send the videos, since obviously I don't have like a canvas that I can post like my Zoom VODs on, I just render it and post it on the YouTube channel, and then I just send the YouTube video link. So that that'll be in the group me if you want to go re-access the stuff that's been gone over, as well as like the formula sheet we're going to make, as well as like if there are any questions asked, because eventually I'm going to open up like the old homeworks and we can go through it, because I know I didn't get 100% on the last homework. I had some mistakes there. Yeah, I mean, he hasn't graded it yet, but I definitely know I made some mistakes, so we got to look over that stuff. Yeah, so then the next part of this just ends up being, some number to the 11th divided by, Ni, which is 10 to the 10th power. 10 to the 10th power. Yes. And you get 63 something. So that's the answer. It's all these things, like these types of questions, I don't feel like this type of question actually helps you with much. Like this doesn't seem like a value we'd be looking for anywhere. Like P over Ni, this, if anything, I feel like the only thing that this is useful for is over here in question 12. But like this type of thing, just P over Ni, it's just solving. You're given some time, you plug it into your equation, you solve for your P, divide by 10 to the 10th, and then you have your number. So these types of questions end up being like more just plug and chug, similar to free point stuff. And then right here, like calculate your ratio of R net over GL at a new time value. So your R net, as is shown right here, is just going to be this, which is what your equation solves for, over this. So R net's just going to end up being whatever the equation ended up being, which is like 3.67 times 10 to the 11th power. Wait, what did I do? Oh, okay, yeah, I realized that. Yeah, that was stupid. But either way, this is just another plug and chug. So this is basically the same, literally the same question here, just with a different time value. So you just got to reevaluate your P. Other than that, it's the same. Now here's a question that's on the homework a lot, and definitely something is going to make us do. It's like quasi Fermi level stuff. So this is also its own formula for each quasi Fermi level, but it's basically the old equation that we would use, just slightly altered to become a new value. So I don't know if he probably has in the PowerPoint somewhere, but I know I have it written down. He just has so many of these. Here's some quasi Fermi level stuff. Yeah, here it is. So here's like the quasi Fermi level like equations and everything. So regardless of like what is the majority or minority carrier, you still have to solve for two. You have to solve for your FP and your FN. In this case, our FN or our FP was the minority carrier. So this, instead of being an NA, would be a change in P, and this would be an ND. But the equation is very similar. It just ends up being EI minus your number through calculator here, and then it produces EI minus something. And then this one will produce EI plus something. But the thing is, here's a stark difference that I was wondering about in the homework. So FP and FN have a difference in sign. And that is illustrated like right here. So regardless of what's majority or minority carrier, this is still going to hold. Your N is always going to end up being over or above EI, therefore it's always going to be plus. And your F of P, regardless if it's minority or majority, is still always going to be a minus, so it's always going to be below EI. So we obviously won't have to draw them for the test because that's not possible. If anything, he might have us like, have a multiple choice for like a couple things or figures and we have to pick the right one. But the only thing he's going to make us do on the test is going to be like this type of problem where he makes you do FN minus FP at the steady state, which is something important to note. Because at steady state, our P is going to be equal to 10 to the 12th. So you just go through and you plug and chug on that with these equations, which we'll put on the formula sheet shortly. And then last thing, we have like these two questions, which are, these are just theory-ish. So if the light is turned on at t is equal to 10 seconds, if the light is turned on at t equals 10 seconds, how long does it take to reach thermal equilibrium? It takes a few microseconds for anything to react. In these types of questions, if you're ever asked how long it takes for something to reach, it's always going to be in the microsecond range. If it's this type of question, it's always going to be microsecond range. Milliseconds is far too long. Seconds is way, way, way too long. And nanoseconds is still a little quick. So it's always going to be on the microsecond scale. He said that in like, I think our 6th lecture is when he said like everything's going to be on the microsecond scale. And then right here is another, like, I think this is a quick theory one. If the light is turned off, that means he turned it off, so we're going to return back to how this equation started. Calculate the whole density per centimeter cubed at time equals 2 seconds. Obviously, we know that it only takes a few microseconds for these materials to react. So, at 2 seconds, it's been a whole second. It's back to being what it was. It's back to being just regular N-doped silicon. So now it's just going to be this question is the same as question 1. Same exact answer, same question, just tricky. It asks it in a weird way that makes you think like there's more work to be done. Now, this type of question can be made more complex by, instead of saying t equals 1 second and t equals 2 seconds, if you made the gap something on the order of milliseconds or microseconds, you would have to actually go through, recalculate p, and then you'd have that answer. But here, you don't even have to do math. It's been too long. But if it was like 1 to like 1 plus like 1 microsecond or something, then you'd have to go recalculate because it would be a vastly different number. It could be really big still. So that's like the entire quiz and everything. So does anyone have any like further questions on like the quiz topics that they'd like to go over? Because
Mostly making sense. Mostly making sense right now.
all right.
I might want to come back to a few things after I actually take the quiz and make my formula sheet.
Well, we're gonna do we're gonna start doing the formula sheet right now. We're gonna go through these are
Yeah.
I went through and I checked where his PowerPoint's topics for this chapter start, and it starts here with lecture 6 with the generation recombination stuff. So this is where like these are the 3 PowerPoints you want to comb through to find formulas, and obviously that's the quiz and everything. So we would start here at the generation recombination for formulas. So I'm gonna get out a piece of paper, and I advise everyone else pull one out because it's time for formula sheet. So if I remember correctly, we could just have a full size sheet of paper. He doesn't really care. Just that it's only formulas and nothing like cheaty, but that's all we
Oh,
really
the formula sheet. How do you write something cheaty on it? Do you say do good to do this?
Yeah, I guess. Well, the thing is, in high school, I had a physics teacher for 2 years straight, and he would always let you have like a little formula card for his tests, like an index card. And the rule was you could put whatever you wanted on the index card. He really didn't care because like really how, as you just said, like how much can you really cheat with like a little card or a piece of paper? And like what I would do is I would bring a magnifying glass with me, and I would write microscopic, and I would write down problem examples from the textbook. And then I would just walk in and I would look at the problem example. But that's not advised here.
Genius.
Yeah, I mean, it wasn't cheating either because it's not like it's the same problem. It's just like when it comes to physics, when it comes to these classes, like you just need to know how to do the math. You're not going to relearn how to do like Cal 3 or differential equations from this class. If you don't know that coming in, you're going to have a hard time. But when it comes to the processes, everything here is learning a process and solution like methods. It's not about learning a new type of math or a new, like it's just having the equations, having your toolkit, and knowing how to do the process correctly. So we start here. So this is something important that we might have to use eventually, because I remember on the homeworks, at least, he asked us drift current. On the test, he didn't ask us for any drift or diffusion current stuff, but he might ask us that stuff on the test. So this is like, yeah, so your drift currents Jn or J drift, J diff. So this is like the full formula for that. And this is treating it like N, but N and P are both the same. You just replace the N with the P or the P with the N. Like it's the same thing. And if you notice here, this dP and this dN is the same thing that becomes the coefficient on the spatial dependency portion of the MCDE. So the reason this is important for MCDE is similar to homework. There was something like this, unless there was that one problem we were given, where the dN and the dP wasn't given, you needed it though. So I personally didn't solve it like this. I don't think it was possible in that question to solve it, because I think there is a constant value for both of these things in silicon. And that's what I just Googled the constant value for dN and dP. But if like in the, I think question 4, he gave us mu p, mu n or something. That means you can use that stuff to solve for these values. So it's good to have like the Einstein relations and just the drift diffusion current just in case we need it. I don't anticipate it, but it's good to have just in case, because these aren't like easy to remember formulas. So these ones are definitely good. So I'm going to get these down as well. So we have J drift. So everyone have a good weekend.
No.
Oof.
I've had a busy weekend that's been studying, homeworks, trying to keep my head on. If Amber had a panic button, I probably would have pushed it by now.
Yeah, I feel I have 3 exams this week. It's gonna be a fun time. I have
I got 2 quizzes and then 3 midterms next week.
Oh well, midterm. Are they starting next week?
Yeah.
Mine are.
If you're in 307, that one's this week.
What? Oh, I'm not in. I don't think I'm in 307.
Cool.
What's that one called?
That's EMAG.
Yeah, I'm not. I think my only EE courses so far, this is my first semester where I have proper EE courses, are this one and circuits,
Ah, nice.
like intro circuits.
Yeah. Bowman or Gatlin or English?
Of course I have Bowman, dude.
Nice. I
Of
love
course I have
Bowman.
Bowman. All my homies love Bowman.
Mhm.
All right, so we have, yeah, so that's Shan, J Drift, and then the Einstein relation is important to have. But beyond that, that's like full stuff for this one, yeah. The has anyone taken the like has anyone gone like farther in the physics branch and taken any of the like electromagnetic stuff or E&M physics stuff?
I haven't.
I haven't either.
Yeah, I haven't met anyone who has yet. Probably my best bet is to talk to physics majors, but I intended to take those 2 E&M classes for a physics minor, but they might be ridiculous, so I don't know if it's worth it. Because I could get off easier with like obviously a different physics class. Supposedly E&M's notoriously interesting. So
Interesting or difficult?
I said interesting to be nice, but difficult would be the proper term. Yeah. So there's that. So there's the relations. Everyone have these like this one. You can really just write down like this one and then just say or P, because this and this are the same, except they just replaced P and N. And then this, the Einstein relation. You can do the same thing, write down one of them and then say or, like P can also be N, whichever you prefer. And then this is him. I think he's going over like quiz 1 stuff here, so we can scroll past the quiz 1 stuff. Yeah. Well, yeah. And then he started with the leaky bucket and the generation stuff. So this optical generation is what we've been working with. So this thing has formulas and everything, but none of us have had to, like, I've had to do this in physics 3. That's what I remember this stuff from. But beyond that, we don't have any use for this currently in class, unless like he hasn't asked any questions like this, so I doubt we'll ever have one. Like, it's good to know that type of stuff, but these types of relations aren't going to be valuable for us quite yet. And then we start stuff like here. Well, this is just him explaining the fact that excess carriers are a thing. So this is non-equilibrium. And here's an important term to know. So far, I'm pretty sure every single one of our homework questions and the examples we performed has been low-level injection. Because remember, I made a big emphasis to say that the majority carrier concentration does not change during our questions. Like all of our questions, the majority carrier concentration is not changing. It just stays the same. And this is something that's like talking about that. So low-level injection indicates that it doesn't change majority carrier, but minority carrier changes significantly, and that's what we're doing with the MCDEs. So this is what this means in a non-equilibrium state. Like you have something, whatever your majority is, its changes are negligible, so it stays the same, and whatever your minority is, its changes are excessive, so the changes take over. And that's what we define as low level. This isn't something like that's something you need like to write down as a formula. You can if you'd like, but it's just like, this is something that you want to know that all the questions that we're doing, it's assumed we're in low level injection. So we don't need to consider any changes in our majority carriers. And then here's like, obviously, if we're in this state, this no longer holds. Law of mass action doesn't hold. It's probably good to have it written down since we did have to use it on the practice quiz. So if you don't remember it, it's good to have the law of mass action written, because he did have us use it, so he might have us use it again. But beyond that, that's as far as we're going to see with this thing, this one. And then he's just starting to explain like optical generation, which this, all the G-optic and everything, this all ends up just becoming GL later, I'm pretty sure. Like he just like, yeah, ends up treating this as optical generation. And that just becomes our GL, which is like a net generation, right? All right, this is just explanation stuff. This is like some wacky writing of the recombination rate formula, like its proper derivation, I suppose. But as we saw, the net recombination rate, oh, that accidentally pulled that up. The net recombination rate was simply up here, if I remember correctly. Yeah, right here, these formulas. Net recombination can be modeled as just like your change in your minority carrier over your carrier lifetime for whatever that carrier is. It has to be the same. The P's and N's always have to match across the board in all formulas. And then, so this is like what he writes as optical generation. So he obviously boxed it. I don't know. I don't think we've had to use this yet, so I don't think it's actually valuable. Like it wasn't on the quiz. It's something that we need to know because obviously everything we're doing here is optical generation. It's all being generated via light. But at the same time, like if we want to solve for R net, we'll use this equation. We don't need to use whatever this is because this has like time dependence. Why do that when we can just use this? So these are quicker and easier solves. So net recombination is a formula you're going to want because this gets used a lot. So R net for P and N, it's the same thing because you just replace your P and your P's with N's or your N's with P's. So you can write down 1 and just say that. Yeah, and that's just that. Yeah, minority carrier lifetime. Yeah, majority carrier density remains unchanged under low level injection. Good thing to know. And that Fermi level stuff. Does everyone have like your the recombination equations down and everything? All right, cool.
Yeah.
Lit. All right, I'm gonna move back to this one where I got sidetracked with that. So here's this is where he starts talking about Fermi level stuff. So you start talking about how the Fermi levels end up getting split into the quasi-Fermi levels, which is this, QFL's quasi-Fermi levels. And in equilibrium, they're equal to each other and they're equal to EF and all that stuff. And this is where he starts saying like, oh, how you compute them. And he's gonna end up with your formulas and everything. Thermal equilibrium versus non-equilibrium. And you have like these massive big equations and everything. And that's like, no one likes these. So this is the end of this slide or this PowerPoint. These aren't the formulas we want. These are stupid. Those are overly complex for what they are. Is he doing examples here or what? Yeah, here's the proper formula there. This is review question. And here's where he does the proper formula for the first time. So we obviously see this thing, and this looks like a monstrosity that none of us want to deal with. And the proper, actually simplified version of it ends up being this. And this holds for both versions, except there's a distinct understanding. Nope, it's over here. Nope, and that pulled up my whatever. Right, yeah. The Fermi levels were down here. Nope, Fermi levels. Where do you hide? Here's where the Fermi level equations are. So it's more, in my opinion, it's more helpful to write them in this format where you're solving for your f of p or you're solving for your fn, as opposed to the other way where they left the EI on the side and everything. So these are the equations that I would use. So it's just this portion right here, this portion and this portion. And it's important to note that whatever your minority carrier is for a given problem, whether it be n or p, all that means is you simply just end up replacing the numerator of your fraction with the, your solution from your equation at any given time or whatever, or any given like spatial dimension. So you just replace that there.
Can
And
you
then
rephrase that?
rephrase what?
Like the last sentence about replacing.
Rephrase it in like what way?
I'm not really sure. I'm just not following what you're saying.
Oh, okay. So in these equations, like, because obviously there's two equations, and whenever you're doing like computing the QFLs, you're gonna end up computing two every time unless you ask for one, but he just wants both anyway. And what you're gonna need to do is whatever your minority carrier is, so let's say it's n, because in this one your minority carrier is n, your numerator of your fraction that's in ln is going to be right here, change in n, which is what you get from your MCDE equation. That's the number you're solving for. So your numerator is this. Because let's say if in this equation, f of p was our minority carrier, instead of it being the number that was given to us in the problem, we'd replace it with change in p instead. And that's the only change you make, because these two formulas aren't necessarily in their general form, because these formulas might be different depending on the question. But the only change that you'd see, and that's what I'm trying to get at, because the only change you'd see in these formulas is what the numerator is. It's either a constant value that was given to you in the problem, or It's the solution, the numerical solution of your simplified MCDE equation at some given time or
Okay.
space.
So NA, ND, or delta N, delta P.
Yeah, it's one
Basically.
of those. And in that instance, if Fn is your minority, this one's gonna have your constant. And then another thing, your F of P and your F of N have one other difference between them, that being the sign here, the sign on KBT. And the sign is important to know because obviously you get the wrong answer otherwise. F of P, regardless of whether or not it's majority or minority, will always have that negative sign because holes are below EI and will always be below EI. And then your F of N, regardless of majority or minority, the formula will always still be positive because the electrons are always going to be above the EI line, the intrinsic silicon line. And that's what this whole thing is, because the reason we compute it like this, EI minus, because at the end, when we graph it, we don't say the line EI minus. No, it's because the reason we say it like that is EI is graphically represented. So we just put the line and then put the space as some positive value between the line. That negative sign is simply to show us where the line is on the graph. And that's what this entire thing means because we're graphing it. So at the end of the day, when you're solving for FP, the answer may be EI minus 0.41 electron volts, but the answer just ends up being 0.41. That's the EI is just a graphical reference point that we use. So these are the important formulas. I'm going to get these down too, F of P and F of N, because in the quiz that we just went over, one of the questions had you compute both of them and then compute, I think it was the ratio. No, not the ratio. It was Fn minus Fp or something. And that, I don't know what that should solve for. It just spat out a number. It wasn't some trick question or anything. You had to use a calculator for it. So that's how that works. Yeah, so these ones, the quasi-Fermi levels at the beginning, they sketched me out. I always had to be during the homework for this chapter, when I looked at the quasi-Fermi level stuff, I was a little intimidated. I was oh, this is a little weird. But then once I went through the PowerPoint, I found this exact slide with this stuff. It's not that bad. It's really not that bad. And when I was doing the homework, I was really hung up on the signs, and I had to confirm to myself, I had to justify why the signs were the way they were. And my explanation that I just gave to you is what I eventually came to. It's the fact that the signs mean nothing more than a graphical representation.
Yeah, that makes sense.
Yeah, because at the end of the
Because
day,
FP's got to be negative.
Yeah, because at the end of the day, that energy level, that FP, isn't negative. It's referenced from the valence shell. It's not negative. It is a positive value of energy. It's not negative. It's just that we reference everything to EI, our zero. So that's how it works, and that's what I eventually came to. So I was happy with that. And it's a good way to think about it. And that's how I just thought of. So then we get to that, and then what other formulas were there, if anything? There's some stuff here. This is the, oh yeah, let's get down to the actual MCDE. This is the proper full MCDE before simplification. This is what we're going to be living by for this quiz. And then after this, we'll scroll back up and go over the two solutions that we know of to the MCDE. So we just get this down. And this same thing with most of these things, wherever you see an N in this one can be replaced with a P if you're doing minority as the holes. This one just so happens to be N, but it's the exact same equation for holes, just every N that you see ends up being a P instead. Which is not bad. Yeah, and then this is what he ends up simplifying it in this question, which is something to look over. Uniformly illuminated optical generations, whatever this is, at time 0, the light is switched off. Yeah, so I'm just going to go through this real quick as a quick example, because this is a special case we don't see too often, that being the fact that in the simplified equation, GL disappeared we don't have a GL in the simplified equation. It's like this. So in this question, it says the optical generation rate, it's been uniformly illuminated with light for a long time. So it reached a steady state and it had no spatial dependence because it was uniformly illuminated. Anytime you see like all the words uniform and everything, you're probably going to end up with no spatial dependence. So you get to get rid of this part. This whole thing just goes away. So the words uniform throughout the volume, all that stuff, that gets rid of your spatial dependence. But then here it says light is switched off. So this GL goes to 0. It's gone. It's no more light. So this special case, oh yeah, and then here it really makes it easy. Assume spatiality, uniform conditions. So this just straight tells you. But even if this part wasn't here, this assume spatiality, uniform conditions, I would still get rid of that simply because it told me the sample's been uniformly illuminated with light, and it didn't tell me special cases like it's damaged or the volume change or something like that. It didn't say that. So that's why it says you can assume it. But then it ends up simplifying. You got rid of spatial, you got rid of the GL, and then the solution for it, the general solution here, is the same one we would use simply without the GL, so it's a slightly modified one. But we're going to go back up to the solution methods for this MCDE because that's what we need to get down next for the formula sheet. Here they are. So as I said earlier, this right here, when you get rid of simply the spatial derivative and only the spatial derivative in the middle, where you get this, it becomes, this is the general form. So we should probably write down both of them just in case. So we'll get this one down first. So this is what I've highlighted as the general form solution. So this is the general solution to an MCDE without a spatial derivative in it. And it's not that bad, which is nice. What's really nice is the fact that he just gave us general solutions and didn't make it that we just have to solve them every single time and do it ourselves, because that would get annoying. Yeah, and then he right here, that example we just went over, like just quickly talked about, where like GL was missing, he has a little note right here, and GL may be 0 if the sample's in the dark. So that one right there was this without this part. That's what it ended up becoming. It was this without GL tau p, which is what, but that can be done at any time, because obviously you can solve the whole thing and then read the question and be like, oh, GL was 0 because the lights turned off? Okay, just cut out anything with the GL, easy. And then as we said though, let's assume that we're gonna use this form and GL isn't 0. We can go back to the quiz up to where that answer was, right here. This is the proper general form for any type of question that's like the quiz. These are this is the most common general form that it's gonna work out to end up being. It's gonna be GL tau p times this quantity. So this, you could what you just wrote down, you can write like an arrow to it and then write this as well. Because this is what it, in my opinion, most commonly comes to in these types of questions.
And what is this one missing? Or is this just
this was
the
just
general one?
This is the general one. This is missing spatial derivative. So look here. This is what it becomes if it's missing just the spatial derivative.
Right.
And this will always work out to become, oh god damn it. So every time I bring my mouse to the top of the screen, I accidentally hit the thing that covers up my tabs. And this will always become this if it's just missing a spatial derivative. If this was missing GL, like it was like the example we just touched on, where GL was 0, it wouldn't be this, it'd be different. It would be that you'd have to take that general form, eliminate GL, and you'd have to solve for A a different way, which would be done through your initial condition stuff. So looking at this is the general form of, this is the solved general form, like with just a spatial derivative missing. If you have nothing has changed except the fact that space, like it doesn't matter, nothing changes with like going along the silicon bar, nothing changes with space. This is what it becomes every single time. It'll always look like this. So this is good to like write this down and say like no spatial derivative or something, because this is a common one that's always going to happen, because it appeared on the homework. I think it might have appeared twice on the homework if I'm not mistaken.
Okay, so this is a further simplification of the one we had on the other tab.
Yeah. So the other one has A, and A is like some arbitrary number we don't know yet. But A will always end up being, in this instance, because our right here, the initial condition 0, So this is like your A is always dependent upon your initial condition. And in this type of scenario, your initial condition being 0 results in this formula. But it's a common one. So it's good to have this like quick simplification down, but like put down, like just remember in your heads, like grain of salt, this isn't the guaranteed answer. This is just a simplification, a further simplification given a scenario similar to this one. Like you could change around all the numbers here, as long as the words are the same, like what it's telling you about this question is the same, this is the answer that you'll get to every single time. So this is a further simplified version when you're missing a spatial derivative. Yeah, all right, let's go back to this. Now there's another solution for when the spatial derivative is present. This is when if time doesn't matter, there's no time dependence, which is what we call the steady state. So I don't remember I'm pretty sure on the homework, if time didn't matter, he said steady state. I don't remember what the other, we might have to look back at that if we have time or anything to like remember, but I'm pretty sure he'll tell you steady state if he wants time to go away. But this is what we would end up simplifying it to, because you eliminate that side, becomes 0. And then this is your general form. And it has its own new parameter, LP, which ends up being this little thing. So it's more complex. And this type of question, like we did this on the homework, I think we did this once or twice on the homework. This becomes this becomes much more interesting to solve because this A and B becomes heavily dependent upon whether or not you correctly identified initial conditions, and not just identified the like numerical values of initial conditions, but also understand like what is and is not possible given some initial condition. Because like when you do these problems and you're solving it, very often, if not always, at least for the ones we've done so far, B ended up being 0 and it canceled this whole side. Because for some reason, this value, because remember, no negative sign on this X, ends up becoming because this ends up being a pretty small number, the LP like quantity ends up being small most of the time. This being small means any type of normal integer in the range of like 1 to 10 ends up making this into a massive positive numerator on E, which as we know is like a pretty ridiculous exponential. This becomes essentially for our purposes infinity. So B cannot be that way. You can't just have infinite whatever carriers, so you got to get rid of it. It goes away. So for the most part, B goes away, but not always. But for the examples we've seen, I haven't seen any examples where B's stayed around. But just for now, I'd put down this whole equation. It's good to have this down because the general form for both of them is good. No spatial derivative and no temporal derivative. No temporal derivative, cool. All right, the general state or general solution of this. Yep. Yeah, and like on the homework, like there was a question where like we weren't given this value dp or dn or whatever, and it took me a really long time. I'm like, well, like we're not given any mu's. There's no way to use the Einstein relation to solve for it here. Like I have no clue what to do here. And then I just was like, I'm just gonna Google it, see if there's like a constant or something. And there was some value for it. It was like 25 or something. And I'm like, okay, cool. Like dp and dn are both constant values for some form of silicon. And I wrote it down, but honestly, I'm not sure if that was the right way to do it. We can look at the homework solution and see, but it might not have been.
Zoom meeting. Study session.
Okay, all right, I'll let you go. I'm gonna go to sleep for a few hours. You know, Sarah's coming home tonight,
Oh,
but she's going to the burn house. She may be sick, so she's gonna go quarantine in the burn house.
all right.
So, Davis and I moved the bed to the burn house.
Mm-hmm.
We're back.
I'm gonna mute him so we don't hear more of that. Here's the boundary conditions determinant. Yeah, so this is him just going over what I just was talking about. Like you always have to use your boundary conditions to determine your A's and B's or whatever. And boundary conditions are also just initial conditions. What I mean. Nope. And then he starts going over problems. So we all have access to these, so I don't see it too important to run through these necessarily. But I don't think really like this type of stuff, like these things, like understanding. Like a very important part of this topic is understanding. Like this type of thing right here, this graph, is basically a word problem. This word problem, like when I read this, I produce a graph like this in my head. Like as opposed to it looking like this, the graph starts at 0 and goes up and then branches off at some asymptote, which ends up being GL tau P in the quiz question. So whenever you read these word problems, if you want to have an easier way like understanding and like making sure you know what's happening, particularly if you want to find your initial conditions easier, it's a good thing to have a piece of paper ready for the quiz and everything, and then like try to draw a graph of what the problem looks like. Because upon reading your problem, like the moment you read your problem, you should be able to graph it right off the bat. You should be able to graph something like this. I can look at this graph and I can tell you that it was at some steady state where there was a light, there was generation, there's your value, and then right here, the light turned off and it starts decaying back to, you know, thermal equilibrium when it went dark. That's what this tells me. But you can invert that. You can be given a word problem and you can write out this graph, and using this graph, you can know in your head, it'll help you out with the problem. And it's something I like to do. Definitely helpful for these types of questions. And then same thing, like when solving for the QFLs and everything, like this whole thing, this is like an expanded version, but I don't think we need to actually use it this way. FNT drops linearly. Let me look at this FN. This is relating it to something. Yeah, this is relating this to this. We don't need to do that. Yep. This is similar to question 3 on the homework. Yeah, all these things. All right, so I think we have everything. Does anyone have any ideas for other formulas that might be valuable? I don't remember having to use any other formulas. Really? Oh wait, there might be one formula. I gotta go grab my homework for that.
Other than the like dark stuff for changing the MCD equation, I don't remember anything.
Yeah.
But that's not technically a formula.
Yeah, that's a theory more than it is like its own formula. I distinctly remember that there was a discussion in the GroupMe about one of the homework problems because everyone was having trouble finding a value. And it was yet again like the mythical dp or dn, and it was important because the formula utilized what was just given up here. Right here, it utilized mu, because like we look at this is an MCDE question, but he gave us mu n here. So why would we need mu n? It's because there is an equation that relates. Oh, it's the Einstein relation. We already have it. Never mind. The Einstein relation, if we remember writing that down, it's like one of the first formulas we wrote down. You can see that the d's, like d values, are directly related with mu. And you can use that if given mu, if you need to find d for any given problem. That's what you'd end up doing here. Because I can bet you $50 that if we scroll down a little bit further, the simplified minority carrier differential like diffusion equation is gonna not, like, it's gonna have spatial dependency. Let's see. Oh, it has spatial dependency. Yeah, so like you can tell if you're given, that's a quick thing to remember. If you're doing the quiz, you open it up and that question gives you this, you already know there's going to be spatial dependency. Otherwise, why would you need it? The only reason that's given is because you need it to solve for the spatial dependency constant or the coefficient. So that's something cool you might want to write down or just like remember in your head. If you're given mu, it's probably going to be a second form where you have a and b. So that's a cool little nugget I just remembered. Scrolling through that, this is it's a simplified. Here's a graph of a given solution. This is semi-infinite or whatever. Semi-infinite. Yeah. Yep, steady state and all that. Cool stuff. given mu again, fun. Yeah, he just has a bunch, like 1.5 million examples on the PowerPoint that are like fully worked out. So if anyone wants to like go through further and look at that type of stuff, they can. Like this is solving. This is like the complex solving for A and B. Like this looks terrible, but we all know the way we would do this on the. What the hell? This guy's crazy. No, the way that I would do this on the calculator, obviously, it probably wouldn't end up being this complex. Is this for diffusion? No. By the way, you just like you're solving by just plugging numbers into the functions and simplifying out. All right. This is him general solutioning everything. Yeah. All right. So, do you want to have any like other ideas or questions or something I'd like to touch on?
I think I'm good.
All right. So we have a formula. So we have a formula sheet made. I'm pretty confident we have every formula that we would need for this test. We went over the quiz and everything. Like went over how to solve for all the questions in the quiz. Even though mine looks horrendous, we know how to get all the right answers for these. And got that. We went through the things, coned for all the equations that are valuable. I'm going to close these out. So beyond that, the last thing we could do is look at the homework. Wait, let me even see if he has that up, shall we? Okay. It'd be in files if you put it anywhere. Really? Is it not up? Doesn't even look like he has the third.
I looked a couple seconds ago and it was up. Like I have it pulled up right now.
I'm going to read. Did you find it in files?
Yeah, it was in files. I'll double check what it's in.
Was it? It might not be in the homework then. Is it in figures or something? Oh well, here when I click this, when I click the overall folder, it's right here. I see the two things. But if I click the homework, it's not in there. So I guess that's some organizational error. We should adjust the solution. We all have the homework before. Yep. So this is just him simplifying. So this is the first one. Oh boy, no spatial. The first question, like question 1 right here, this whole first question is basically what he made our practice quiz. Like this is, from what I can see, in the practice quiz, we simplified this and it became this exact thing. We specified initial boundary conditions, which yes, it made us specify the initial boundary condition, the only one that existed, which is that at time 0, we have 0 carriers generated. That was part of that quiz. We solved the simplified MCDE, which got us, where was it? Which got us this version of it right here. This is what we had to do on the quiz as well. We did that. Then we found the electron and hole density at the steady state. I don't think in the quiz he asked for that specifically, but if he did, the way you would do that, obviously at steady state, as I said, remember, think about it like a graph or draw it down as a graph. This right here is him finding for his steady state, or what you could use to find steady state, which you can say at steady state, time is at infinity. It's gone on so long that it's reached a constant state or a steady state. And in this case, you can see that he says it approaches GL tau p. That's the exact same scenario as we saw in the quiz. So question 1 on the homework is, as far as I'm concerned, just the quiz. What he made the quiz, like the practice quiz. We find the electron hole densities. We did that on the quiz to an extent. Then we did ratios of it. Provide the sketch of the steady state energy band. We don't have to do that, but I recommend doing it regardless right at the bat after reading the question. Find net recombination rate. We did that. And then here he says specifies at the steady state and then at some given time. So we also had to do that in the quiz. Same exact thing. We did that. We found the recombination rate at 2 different times. Here we found it at time less than 0. It was 0. We found it at time is equal to 1 second. It was just equal to 1. But I forgot to multiply GL by tau p. I'm a genius or something. I don't know. And then same thing here. We have another recombination rate divided by GL with some other new given time. So we did it 3 times in the quiz. So the homework is extremely similar. Homework question 1 is extremely similar to what we did on the practice quiz, like question for question. And then here, this is an example of one where spatial derivative and the GL turn to 0. So without even reading the question, I can look at this part right here, and I can know that the graph's probably going to look like constant held value of GL, and then the light turned off and it went like this. So let's look down. Oh, what do you know? At some time t, it was at some initial value and it dropped. So when you look at these questions and you read them, you can start to realize that every single question, every word question right off the bat, upon reading it, you can immediately do this. This doesn't have to be like part D. This can be part A. You don't need numbers for this part. If you want to put exact values, maybe, but beyond that, like this type of thing can be done instantly, and it's definitely helpful to know what the graph in your head looks like. So this is like an example of obviously spatial and GL went to 0. That was that. Now this is the one where it was broken. So this has heavy spatial dependence, and this also said what? Yeah, so the spatial dependence was based on the minority carrier lifetime, or no, yeah, something about it. So x is equals 0. Minority carrier lifetime was 0 at x equals 0. And then greater than the minority lifetime became a constant value. So right here, there was no carrier lifetime because it was broken. And then over here, the carrier lifetime existed. So here you have some spatial dependence. You have your boundary conditions right here, which you... Yeah, so right here he specifies that initial conditions for time dependence, but boundary conditions are for spatial dependence. Yep, all right, that's all pretty basic. Here's something that's interesting to see. So I probably didn't get this right on the thing. So this right here, the fact that Fn changes over some small period, I believe he explained this as saying, well, right here, he does this, and he proves that NA obviously is majority. It looks like it stays the same. Yeah, and that should be something different there, or the same. So it's Fn. So this is the one where it's damaged. So the Fermi level changes because of it being damaged at some given value. So at x equals 0, the carrier lifetime was 0. That was the only thing that was directly affected. So for some reason, the carrier lifetime being 0 for electrons at some given value x, which happened to be 0, results in the Fn and Fp being identical at 0. And then obviously Fn gradually changes back to being identical to EI. I had it equal. I got the part where it was equal to NI in the homework, but I did not get this part where it like had some level of separation. But I doubt that's going to be
Same.
Yeah, because obviously this part right here on the quiz, unless he makes a multiple choice question that we haven't seen yet, where he has figures, then you have to take a like this would be a like A would be like this picture, B would be like a different picture of this, which I don't think he's going to do. He's going to make us do ones like this, like down here, like find the value of Fn minus Fp at some time value. In this case, he happened to stay steady state, so that's like time equals infinity. So in this case, you would just solve Fn and Fp and then get your integers. So you don't really, I don't understand this wholly. Like I can say that I don't fully understand why that they were started here and then approach. I understand why it's at EI because the math was right there. I get that. I just don't know this part. But I also know that based on what the quiz has like shown, like the practice quiz and the stuff we talked about, I also know that this is not going to be on the quiz in any way, shape, or form. Like this is not going to be something that you can lose points for. So in the long run, it's definitely something that it might be worth like asking another question to get clarification on just for your own understanding. But for the purposes of the quiz, I don't think this matters. So we're just gonna skip it. Yeah, and then question 4 was what? This one. So what, lights on, lights off? Is that what we're looking at? Yeah, this was the one where it had like, yeah, this was fun. This one had a bunch of weird relationships. And it was, we can see right here all the, like, this one's really weird and it sounds odd, but it's because it's giving you a bunch of boundary conditions in an awkward way. Because obviously, like, when we specify initial and boundary conditions, we have no time dependence. We got rid of that because it said steady state somewhere. Yes. And then we get to our boundary conditions, which means spatial boundary conditions, and we plug in 0, you plug in infinity, and you get that at x equals 0, you have something generated at the surface of the bar, and then at whatever distance far down you go away from that, nothing's being generated because the light goes nowhere. And because of that, it looks like this. So all these ones are just, you know, just the way they are. So that's all I got for those ones. It's we have like the full written solution. It's all numerical. There's not much I can explain there unless there's like any specific questions, but I might not know the answers necessarily for these. But for the purposes of the test or the quiz, whatever we prefer to call it, like this type of question, while it could be given, the simple fact that the nature of how these tests are given, because taking a quiz is as much a test of you understanding how to take a quiz as it is a test of you understanding the material of a given quiz. The nature of like a Canvas quiz or a lockdown quiz that's being given the way it is, like remotely and online, this kind of thing, is the fact that like it's fill in the blank or it's multiple choice. And that's restricted based on what it is. Like this question can only be multiple choice because unless he wants to go through and individually grade every single permutation of how a student could type this in, you're going to make a multiple choice. This is a lot easier. But this also restricts the difficulty of the question, because as I said, question 3 is much, much, much easier than, you know, if you go in with no information, very little information, you can answer this question much easier than you can answer, you know, part A of any of these given questions on the homework, because the homework doesn't restrict your possibilities. But as I said, I feel like this might be more difficult. But even then you get to like questions like these where it's like typing in, like if it's just like this, it's probably going to be an integer. Like you look at this question, you can tell probably right off the bat that this is going to be something simple like 1 or 0, because it doesn't say round, it doesn't say like it's just going to be 1 or 0, and it ends up being 0. And this is just like test taking rules. And then you go to this. This is another thing. The difficulty of the question is restricted by the medium it's being given. This is also pretty damn easy because as we see, the only changes here end up being literally he just moves signs around, it looks like. We know that the general form has to be a minus. So these are already cut out. And then we know that the E has to have a negative, and this one's a positive cut out. So as it like the way that these tests are given restrict the difficulty of some of the questions, and they make it a lot like more given. Like the test is easier than the homework simply because of its medium. It's not handwritten. Like if we were on campus taking this class how we normally would, this would be much harder than it's going to be, simply because it's restricted in its
You're
difficulty.
right.
Yeah, no, like the nature of how I take tests changed simply because the medium has changed, and the medium restricts the difficulty of certain questions and problems. And this is something that you can use and understand across the board for all online classes for as long as you continue taking them. The medium of the test is just as important as the content of the test. And then we get to like these types of questions. Like these are the reason we have questions like this. Like on the homework, we weren't explicitly asked like A through F of calculate this, because these are things that are just like something that once you have P, of course you'll be able to solve for this. This seems like something that makes no sense. But here, like we need something to fill space, and we need something like this, and we need something to like test theory, but also like give you some type of calculation to do. this should be 1. Same like question 2 should be 1. Simply, this is just testing that you understand, oh, we're at low level injection. Your majority carrier is not going to change. So, something divided by itself is 1. That's like, these types of questions could have been multiple choice. But if you think about it, if question 7 or question 2 was given in a multiple choice format, it would make it easier. Because if you see this and you're stuck and you're like, is that 10 to the 10th, is that 10 to the 18th, but then you see 1 is an answer, you're going to pick 1 because it's going to be like, oh, if that's an answer, that means it's divided by itself. Yeah, making it open-ended increases the difficulty of the question when it actually is a really simple question. So this type of medium can go both ways. This restricts the difficulty of the question because it eliminates possibilities of the student messing up. Like if this was open-ended as opposed to being multiple choice, you might have accidentally eliminated time instead of space, and everything else would be wrong, and then you'd mess this up too. But no, this makes it easier. But then these have increased difficulty, or on par difficulty with what they would have been if you were taking it, on paper. But at the same time, I don't believe this type of question would be asked anyway. Except right here, this is something that, like, I looked at this and I realized that this is this value P divided by intrinsic silicon is actually what you put inside the natural log for calculating f of P. So this is a value you'd calculate eventually anyway, if you need to calculate it at that time. But this one is just, like, in my opinion, useless. It's just 1, but it's just verifying that you understand theory. But yeah, so that's all I got for like just test taking strategies and quizzes stuff. Like, there's limitations to the medium, and if you learn how to like exploit and understand them, then you can perform better overall. Like, college is just as much a test of how well you can understand how to take a test as it is a measure of how well you can understand your material. And that's a life lesson for you if you didn't have it already. I got given to that by my SAT tutor in high school. Man was a legend. Absolute legend. All right. Well, anyone got any further thoughts or stuff they want to go over? Because otherwise,
I think I'm good for now.
all right. Feel free to like send questions before the test or anything like that, and I can try to answer them. But obviously, if you send it to the group me, you'll get answers not just from me.
Mm-hmm.
Yeah.
I appreciate you doing this, man.
And this helps me just as much as it helps you. Like, I don't come into this as like a necessary expert, but when I start, the thing is, for me, I learn extremely well if I explain something. If I have a mediocre understanding of a topic, as I explain it to someone, my brain will work overtime just to make myself not look stupid.
Yeah,
So
I'm the same way, except I don't have the mediocre understanding of this topic.
Yeah, it'll figure it. It'll work the problems to figure it out just so I don't look like an idiot. That's how it works.
Nah, I get that for sure.
I'm grateful for it. Yeah, no. So, and then obviously, like, having this recorded, then everyone else can watch over it, and I can watch over it myself.
Yeah.
Yeah, this has been great. Thank you.
Yeah, it's been
Very
really
much.
awesome.
Yeah, I will. I'll save this and it'll be uploaded and it'll be a YouTube video, and I'll post the link to that in the group me if anyone wants to go over it again. If they need to look back at something or need a better explanation, that kind of stuff.
Cool.
Heard.
Oh, I just got a notification that what is it? TikTok has been the TikTok ban has been temporarily blocked. Okay.
Oh man.
Oh, did Walmart buy it? I was hearing something.
I
like
thought
that.
it was a toss up between Walmart or Oracle, but I also saw something that Walmart and Oracle might be working together. So.
Oh, that'll be interesting.
Yeah. To purchase.
Also, why Walmart? That makes no sense to me.
I figured it'd be like Facebook or something.
Yeah, like Facebook. You know, like
Something
one of the other
Social media
medias.
tech company or whatever.
Who could know?
Walmart.
It's weird.
I mean, who cares? I've never even downloaded the app, so it doesn't really make
Yeah,
a difference for me.
It has legitimate security concerns, but at the same time, like, it's just a big thing.
Yeah.
It's a complex situation.
It is.
Yeah. I mean, we're gonna get looked at.